Dear students, now we will start with our second unit of industrial electronics. In this unit, we study the operation amplifier circuits, its block diagram representation, applications of op-amp, and some of the features of operation amplifier. The operation amplifier is a device that can be used to amplify DC as well as AC input signal and was originally designed for performing mathematical operations such as addition, subtraction, multiplication and integration. With the addition of suitable external feedback elements, the modern day op-amp can be used for a variety of applications such as AC and DC signal amplification, active filters, oscillators, comparators, regulators and others. So, you can see here the symbol of an operation amplifier. An operation amplifier will be having two inputs and one output. The two inputs, one is plus marked, that is the plus marked input terminal is called non-inverting input terminal. The minus marked input terminal is called inverting input terminal, and this one is the output terminal. That is the most often used symbol of an operation amplifier. Sometimes some people will be showing the op-amp symbol along with the power supply also. For an op-amp, as you are used to differential amplifier, a plus and minus power supply should be there. Plus VCC and minus VE. So sometimes a symbol of an operation amplifier will be having plus V plus and V minus supply voltage be included. So you will be having two inputs. One is inverting input, other one is non-inverting input, then a positive power supply and a negative power supply. So that is the symbol of an operation amplifier. Now we will discuss about the block diagram of a typical operation amplifier circuit. As I told you, an op-amp is a multi-stage amplifier. It can be represented by a block diagram like this. See, it is having four blocks are here: input stage, intermediate stage, level shifting circuit and output stage. Input, we will be applying to the input stage. We have two inputs for an operation amplifier. As I told you earlier, it can be inverting input or non-inverting input. Now you can see down, the input stage is a dual input, balanced output differential amplifier. Second stage, intermediate stage, it is also a dual input, unbalanced output differential amplifier. The third, level shifting stage, it is a emitter follower with constant current source. Last one is a complementary symmetry push-pull amplifier. See, all the stages you have a differential amplifier. That is, the first stage, input stage, is the dual input balanced output differential amplifier. This stage generally provides most of the voltage gain of the amplifier. So, input stage provides most of the voltage gain of the amplifier and also establish the input resistance of the operation amplifier. So you have seen that all the stages differential amplifiers are there, and now you must be understood why we studied the differential amplifier as unit 1. It is the basic building block of an operation amplifier. Operation amplifier consists of many differential amplifier in different configurations. So that is the reason our very first units discuss only about different configuration of differential amplifier, and our first lab experiment is also on differential amplifier. Now move to the second stage of op-amp operation amplifier block diagram. The second stage is called intermediate stage. It is again see another differential amplifier, only case it is unbalanced output. So it's driven by this differential amplifier will be driven by the output of the input stage. The first stage output is driven by the first stage output. Most of the amplifiers, the intermediate stage is a dual input unbalanced output, mostly either dual or single ended it can be, and here direct coupling is used. DC voltage at the output of normally DC voltage at the output of intermediate stage is well above the ground potential. It will be sometimes your output voltage will be sometimes shifted. Output voltage will be sometimes shifted. So next of our third stage is a level shifting circuit. Generally, the level translator circuit is used after the intermediate stage to shift the DC level at the output of intermediate stage downward to 0. So normally direct coupling we are using in this stage. Because of that, sometimes its output will be well above ground potential. So in order to downshift level, you need to shift it back to 0 potential. We are using the level shifting circuit. See, that is again an emitter follower with a constant current source. The final stage is usually a push-pull amplifier output stage. The output stage normally increases the output voltage swing and raises the current supplying capability of op-amp. A well-designed output stage provides low output resistance. So when you are studying about features of op-amp, we can see that input impedance of op-amp is very high because we are using a differential amplifier here, and output impedance of op-amp is very low, or ideally you can say it is 0 because output stage will be providing a low resistance. From this discussion, it is clear that most of the stages of op-amp is made of differential amplifier in different configurations. So that's on block diagram of an op-amp. Now we will move to the pin diagram of op-amp. Normally op-amp will be available in MU-A741 IC. It is an 8-pin IC. See, 1, 2, 3, 4, 5, 6, 7, 8-pin IC. In that, pin number 2 and 3, I told already that for an operation amplifier we have two input. One is inverting input, other one is non-inverting input. So the pin number 2 and 3 of the operation amplifier is inverting and non-inverting input. Now your output is pin number 6. Now what else was there? You have a plus power supply and minus power supply. Pin number 4 is the minus power supply. Pin number 7 is the plus power supply. Normally we will connect only these many pins. Pin number 2 and 3 for input. 4 is the 4 and 7 for power supply, and 6 is the output. Pin number 8 we might be connecting. It is not connected. Pin number 5 and pin number 1 are called offset null. That is also normally we will not connect. And regarding the offset voltage is there, offset current is there. At the end of this unit we will be discussing about those things. So that is the pin diagram details of an operation amplifier. Now we will move to the next slide. So it's again a general introduction only is giving on here. Just this is a general symbol of an op-amp. It is having a non-inverting input and an inverting input, plus minus. This is the output. This is the basic op-amp symbol. Typical uses of an operation amplifier is to provide voltage amplitude changes, amplitude or polarity. Oscillator we will be using. Filter circuit we can form with operation amplifier. Many type of instrumentation circuit we can form with operation amplifier. What are the typical applications? Now we'll move to the next slide. Now we discuss about the single-ended input. Single-ended, see this operation amplifier. Your non-inverting terminal plus terminal, you are connected an input of sine wave. Inverting terminal is connected to ground. So two input terminal, only one you are connecting input, other is grounded. So it is called a single-ended input operation. So since you connected your input to the non-inverting terminal, your output, of course it is an operation amplifier, it is amplified output, and you are connected to the plus or non-inverting terminal, your output is just an amplified version of your input. There is no polarity change because you connected to the non-inverting input terminal. Now suppose, see the next figure, this one. Here you connected plus to grounded. That means non-inverting terminal you are connecting to ground. Inverting terminal you are connected a sine wave. Since you connected input to the inverting terminal, your output, of course it will be amplified, but you see the phase is shifted. Here start from positive to minus, here start from negative to positive. So output will be having a polarity change when you connected to the inverting terminal or minus terminal of input. That is single-ended operation. So at a time we will give input to one terminal only. The other terminal will be grounded. Next, double-ended input. Now you see here, you will connect input to plus terminal and minus terminal. So the output will be a difference between these two input. That means plus and minus. So this is a V input 1, this is V input 2. So difference between these two, that is VD, is V input 1 minus V input 2. That will be amplified. Or that is only shown here. The difference only shown here, that is the VD, and that will be amplified without any polarity change. And here also just see, always when your polarity not changing means you should subtract in such a way that V1 minus V2, plus should come first, minus should come the next. So V1 minus V2, that is called double-ended input. Now there can be distortion. See, you are providing here an input and you are giving here your plus VCC and minus VCC. Now see here plus 5 volt and minus 5 volt. So peak to peak 10 volt. Now suppose if your output exceeds 10 volt, it will be clipped. See, I am giving some input here and it is amplified here, and this, if the output exceeds this 10 volt, that means plus 5 up, plus 5 down, surely it will be clipped. You will not get that portion. So that is the reason when we did the differential amplifier in the lab, I told you to give the voltage of differential amplifier in millivolt range. If you are giving a high voltage, when it is getting amplified, surely the transistor can go to saturation level and your output will be clipped. For that reason only I told you, you give voltage in millivolt range. You all must have given 10 millivolt peak to peak. Some must be given 20 millivolt. So this is the reason. If the output is exceeds the, we do know the gain of the amplifier. So sometimes the output can exceed this supply voltage, surely we will be getting output distorted.